This 1997 OBS Chevy truck maintains the exterior profile of a classic analog workhorse, but underneath the sheet metal, it is running a Gen 4 LS3 engine mated to a ZF 8HP transmission. Inside the cabin, the original analog 90s dashboard sits right alongside a modern sequential shifter and a Blink Marine digital keypad. That modern interface exists to command the ZF 8HP, which replaces the legacy 4-speed 4L80E automatic. The performance leap is strictly objective. The 8HP provides 8 forward gears, shifts in 0.15 seconds, and cuts 60 pounds of mass. But capturing those metrics is a massive engineering hurdle. Unlike older transmissions, the 8HP is completely devoid of mechanical shift linkages. It is a true fly-by-wire node. It cannot function without a continuous, high-speed stream of digital data, dictating torque requests, throttle position, and engine RPM. How do you integrate a transmission that demands a high-speed vehicle network into a 1997 chassis built with physical wires and vacuum lines? Integrating the 8HP requires a complete rebuild of the vehicle's systems architecture, moving the project beyond the scope of a traditional mechanical swap. Realizing the mechanical benefits of a modern powertrain requires abstracting the physical hardware and building a programmable logic network to control it. The first prerequisite is physical, mating the Gen 4 LS engine to the ZF 8HP case, which requires an aftermarket adapter plate. The torque converter interface demands exact precision. A custom crank pilot bushing adapter must be installed to ensure proper depth. Ignoring this measurement has severe mechanical consequences. Improper alignment translates directly into driveline vibrations, shattered flex plates, or destroyed transmission pump gears. The physical footprint introduces further constraints. The 8HP case is wider and taller, frequently requiring the vehicle's steel transmission tunnel to be cut and expanded. Moving backward, the driveline must be adapted. The 8HP utilizes a unique output flange, dictating a custom driveshaft fitted with a CV joint. Even basic parking requires a physical workaround. The 8HP's internal park and neutral lockout strictly requires active hydraulic pressure to release. If hydraulic pressure drops, the transmission locks. A manual override mechanism must be physically actuated underneath the vehicle just to move it. These physical modifications serve a single purpose. They act as the hardware abstraction layer, bridging the mechanical gap so software integration can begin. With the hardware mated, the system needs a continuous high-speed communication loop to feed the transmission the telemetry it demands. The build utilizes a CAN bus topology, a digital network linking engine management to the dashboard and transmission. The Max ECU standalone unit acts as the host, generating the primary data stream. To prevent data reflection on the network, termination status is handled internally via software jumpers, completing the circuit. From the ECU, the CAN data line routes to the first pass-through node. This Dakota Digital BIM module serves as the critical translator. It intercepts high-speed CAN data, translating it so the analog dashboard displays accurate telemetry. Returning to the network map, we establish the final interactive endpoints. One data line routes to the Blink Marine keypad, receiving physical inputs. The final line splices into the 8HP transmission. This hierarchical network topology allows a 1997 chassis to supply a modern transmission with the precise telemetry required to execute a 0.15-second shift. Stripping out the mechanical 4L60E transmission triggers a cascading consequence, the physical loss of legacy auxiliary switches, including the mechanical trigger for reverse lights. Instead of fabricating custom brackets to mount new analog switches, the build relies on I/O reprovisioning. The Max ECU replaces physical switches using programmable logic gates. The reverse light integration demonstrates exactly how this software solution works. On the ECU breakout harness, pin 8, General Purpose Output 5, is programmed to route a ground-activated lead directly into the factory C200 wiring bundle. Based purely on gear data broadcast over the CAN bus, this logic intelligently triggers the legacy reverse relay beneath the dash, bypassing the need for a mechanical switch. At the driver interface, the sequential shifter provides digital inputs to the ECU via a blue wire for up and a brown wire for down. Because these inputs route through the ECU first, their functionality is completely flexible, allowing these hardware inputs to be remapped to trigger entirely new features. Cruise control is completely re-provisioned. If the driver holds the sequential shifter backward at speeds over 30 miles per hour, the system activates cruise control. Pushing the shifter forward during cruise mode then increases the vehicle speed in precise 5-mile-per-hour increments per hold. By centralizing logic in the ECU, the build circumvents legacy hardware limitations, transforming a basic shifter into a dynamic command interface. The scale of this integration is significant. Over 50 hours were spent purely on bench testing and schematic planning before a single wire was installed in the truck. That bench testing is mandatory for mapping analog elements into the digital network, like ensuring a 100 psi analog fuel pressure transducer correctly feeds digital data to the ECU. This process highlights how modern vehicle capability is no longer dictated strictly by the sum of its mechanical parts. The successful integration of the ZF-8HP perfectly embodies this transition from physical-mechanical linkages to a highly networked, software-driven architecture. The physical integration hides this complexity entirely. Elements like a custom 3D-printed C200 wire pass-through neatly bridge the dense data networks from the engine bay straight into the cabin. By establishing a robust CAN topology and utilizing centralized programmable logic, a completely analog legacy chassis has been successfully resurrected as a modern, software-defined vehicle.